Now that we have discussed the theoretical aspects of a one-way MANOVA model, we are now looking into the practical example with real life data. We have at hand the US data of hospitals. It's hospital data. These hospitals have been grouped according to two factors. One is ownership and the other is the certification level. Both the factors having 3 levels each, and then what we do is we are testing the effectiveness of ownership, that is one of the factors at the moment, because we are considering one-way MANOVA model. So, we are testing the effectiveness of ownership of factor of the hospitals on the different cost aspects, cost to the hospitals. So, since this is a multidimensional case, we are taking more than one cost, but then again to restrict the data dimension, we are considering about 4 costs to the hospitals, so that we are keeping the data dimensionality to 4. Okay, so what we had already said in the last session, that we have in a certain US state, hospitals are classified on the basis of ownership and certification. There may be more factors, as I have mentioned, but let us say that at the moment we have data classified in these 2 groups, out of which only one we can test at the moment, because we have the knowledge of one-way MANOVA, and the study is basically conducted to investigate the effect of ownership on costs to the hospitals. So, I said I would introduce the cost factors. So, we have the first one. So, these are the different costs. First one is, so basically 4 costs were 4 types of costs were monitored. Okay, and data were collected on them. The first one is the costs of nursing labor. The second one is the dietary costs, how much each hospital is spending on these aspects. Then we have X3, the third one, the plant operation and maintenance costs. Plant, essentially the hospital, plant operation and maintenance costs. And finally, we have the cost of housekeeping and laundry. Right. So, we would like to see whether the ownership factor and these costs, what is the level of effect of these costs on the ownership factor. The ownership factors being private, non-profit organizations and government. So, from this, all I know is that I have P equal to 4, that is the data dimensionality. So, about the data, what can I say? That I have P equal to 4 cost variables of a total of n, that is 516 observations. So, this value gives me the total number of hospitals that have been covered. We still do not know how many are there in each level of the factor. So, now we have these were separated, these observations were separated according to ownership, again to stress upon which factor we are considering at the moment, and in K or 3 groups. Obviously, because it's ownership, we have 3 groups, K equal to 3 groups, and some more information are given to me. I have given that N1, that is under the first type of ownership, I have 271 observations. Under the second one, I have 138, and the third one I have 107 observations, giving me n equal to 516. So, I have this is the data from number of data points from each category of ownership. Now, we have the, so basically what is given is not the data in totality, we have here the compressed data, some compressed data, which is obviously good enough for me to do the analysis. This is common in situations where the dimensionality is high, we need not write the or take help of the whole data at every point, at every level of calculation. Some compressed information is good enough for my analysis. Sometimes this will become mandatory if say the data are a little sensitive, say I have included one variable which is a little bit sensitive, which includes some such information which are not to be disclosed at the very ground level. So, what I have is the compressed data of this type. So, I need to know the group means. Okay. So, the group sample means are given to me, group sample means. I have to have these obviously, without which I cannot proceed further. So, the first one x1 bar is given by 2.066, then I have 0.480, it's 4 dimensional, let me make it bigger, then I have 0.82 and 360. So, basically here I am getting the first one, say 2.066, this is giving me the sample mean on the of all cost, the first cost x1 in the first coming in the first group, that is the first group is probably the private ones. Okay. Second is second element is that of the same group, this is x1 bar, but this is pertaining to the second type of cost. So, similarly I have the for the second type of ownership I have x2 bar, and these values for the 4 variables, for the 4 cost variables are 2.167, 0.596, 0.124 and 0.418. And then I have the third group sample means, these are 2.273, then I have 521, 125 and 383. Since I know the NI's and I also know the XI bars, I can calculate, even if this is not given, therefore calculate the sample mean, the overall sample mean X bar as 2.136, and then you have 519, 102 and 380. I also have the given the sample variance covariance matrices. So, again instead of the individual data observation, I have been given some compressed information, the sample sizes in each category, the group sample means, and then I have been given the sample variance covariance matrices. Okay. So, the first one I am using the notation S1 for this. This is a 4 by 4 symmetric matrix with elements like 0.291, then I have minus 0.001, the next one is 0.011, 0.002, this is 0 being kept to 3 places of decimal, 001, and then I have 0, this is 010 followed by 003, and the last element is 0.010. And similarly, I have S2 and S3, these are also given. Okay. Otherwise, again I cannot proceed. So, I have been given these 3 sample variance covariance matrices. I can see I know that Si, if you say it for the ith group, then this is Si is nothing but 1 by Ni minus 1, and this is how I define the sample variance covariance matrix. So, Xij minus Xi bar prime sum over j's from 1 to ni. So, what I need after this, just as after these group means I have calculated the overall sample mean, similarly I need to calculate my within matrix, for which I need the each of these individual sample covariance matrices, so that I am able to calculate the within matrix, okay, within variability matrix, which we have denoted by W. So, what is that? It is nothing but, therefore, calculate, again we can calculate this matrix W. I am interested in W and B, because these are coming, these two are the matrices where my interest lie, because these two are coming in that likelihood ratio criterion lambda star. So, basically I have to arrive at these two. B, I can see I will get it with these mean information. For W, I will have to calculate it with the help of the sample variance covariance matrices, and this is nothing but n minus 1 S1 plus n2 minus 1 S2 and n3 minus 1 S3. So, this is, since, well, you know that this is nothing but the Xij minus Xi bar, Xij minus Xi bar transpose this matrix. Okay. So, this is equal to this, and with each of the SIs having been defined in this way, W matrix is nothing but this matrix, which can be calculated with the help of the NIs and the SIs. And what about B? Well, B is also, it can be calculated with whatever information I have with the compressed data. This is nothing but Ni times Xi minus X bar, Xi bar minus X bar transpose. I goes from 1 to k, in this case it is 3. Okay. So, now we test the hypothesis. We are interested in the hypothesis that tau 1 is equal to tau 2 is equal to tau 3. In words, I say that there is no ownership effect that is no differences in the average costs among the three types of hospitals. So, my assumption is this: whether it is a private hospital or a non-profit organization or a government hospital, there is basically no difference as far as average costs pertaining to those four factors are considered. So, that is what my null hypothesis is, that there is no ownership effect and on these costs which I have considered, okay, among the three types of hospitals. Right. I know that the test statistic criterion etc. for this is the Wilks lambda, if you recall, is given by determinant of W by determinant of B plus W. Now, in the MANOVA parlance, again W is nothing but the within or residual sum of squares cross product matrix, and B is the between or the treatment sum of squares and cross product matrix. So, if you wish, you can just skip it here, that W is the within or residual sum of squares cross product matrix, and B is the between or the treatment, in this case this ownership factor, the treatment sum of square cross product matrix. So, this is the Wilks lambda criterion given by determinant of W by determinant of B plus W, and since W and B they depend only on the data, I have all these values to me, I have the matrix with me, and this value comes out to be 0.7714. All I have to do is calculate the determinant of two 4 by 4 matrices. Now here for p equals 2, this is for p equals 2 because we have, no, not p is the data dimensionality is 4 and k, the number of groups, is 3. Can we use any exact test? Yes, we can. The exact test for, well, we have listed the situations where we can use exact test, and we can use the exact test for the situation where I have p is greater than equal to 1 because I have p equals 4 and k equals 3. This case can be used, and what is the test statistic for that? So, can be used, and the test statistic here is n minus p minus 2 by p, this with 1 root lambda star by root lambda star, and this gives me, I have n as total number of observations, that is 516, minus the dimension minus 2 by the dimension, and then I have calculated the Wilks lambda. This is root of 0.7714 divided by this, giving me the value 17.67. Okay. That is the observed value of the test statistic I have from the data, and this test statistic is following an F distribution with degrees of freedom twice p twice n minus p minus 2 under h naught. So, this has to be compared with, I have to compare this with f 2p is 4, and then the second degrees of freedom turns out to be quite high because n is 516. So, this is 1020. Now, you will hardly have any table where this has been tabulated. What we do is we use that this is approximated by the chi-square distribution, central chi-square distribution with 4, not 4, we have 2 times p. So, I have 8 f8, the first one. So, this is chi-square, central chi-square with 8 degrees of freedom, but divided by that 2p. So, this is getting divided by 8. So, this observed, the tabulated value, observed f is 17.67 and the tabulated chi-square 8 at 0.1 say. So, basically I will have this f8 1020 at 0.1, this will be approximately equal to 1 by 8 chi-square 8 at the same level. So, this tabulated value is equal to given by, the whole thing is given by, divided by this is given by 2.51. So, I am calculating, I am comparing 17.67 with tabulated this by 8, and this is obviously greater than or equal, greater than this 2.51, telling me that I can reject, therefore, reject h naught at 1% level of significance, and conclude that average costs, at least the costs that we have considered, the 4 types of costs, they do differ, average costs differ depending on type of ownership, which is somewhat logical depending on type of ownership. So, you may say that why are we insisting on the exact test, because here n is sufficiently large, n is equal to 516. So, obviously, we can use the plain Wilks criterion or with the Bartlett's correction. So, let us also do that, so that we have the plain directly we are going to the chi-square test without going to the chi-square via the F test. So, let us check what happens then. Let us calculate afresh the test statistics. Now, since here n is large, so we can simply use asymptotics tests, and let us say the one with the Bartlett's correction. The test statistic is nothing but we have minus of n minus 1, and then the factor that comes is p plus k minus of p plus k by 2, and then it is log of determinant w by determinant b plus w, and in this situation this is the constant term is 511.5 with log of, we already know that factor is 0.7714, and this is having the value 132.76. Now, this chi-square test, this test statistic follows a asymptotically follows a chi-square distribution with p times k minus 1 degrees of freedom under h naught, and we have to see that tabulated chi-square p is 4, k minus 1 is 2, so chi-square 8 at 0.01, and this is nothing but 20.09. So, we have already used this value in the earlier situation, and since observed chi-square, that is 132.76 is greater than the tabulated value, tabulated chi-square 8 at 0.01, that is equal to 20.09. The asymptotic test also we reject h naught at 1% level. So, we see that this is not a big deal, though we had some information about the exact test. So, we found a situation which matches with the situation that we had, so where we can take help of the fact that p is greater than equal to 1 and k is exactly equal to 3. So, we took the help of that to go to the exact test. We came to the F statistic, but there also we used some approximation because the second degree of freedom was too high. So, that was again approximated by the chi-square, and we reached the conclusion of rejection of h naught. Now, without going that way, without going through the exact test, we came to our approximate test because n is clearly large here. We went by the Bartlett's correction and saw that in this way also, if we use the asymptotics test also, the hypothesis is rejected, and there is definitely ownership effect on this average costs. Okay. Now, we had mentioned that we have data which have been separated according to two factors, that is ownership as well as certification. So, though we had data, we could not use this information at that level because we only knew how to handle one-way MANOVA. I said that if somebody is interested in knowing that what is the effect of ownership and certification, and obviously an interaction effect of the two factors, then we have to go to the two-way MANOVA. So, let us go into the theoretical aspects of two-way MANOVA, and then with the help of the data, that is the extra data that we need here, the data separated due to the certification of the different hospitals. If we have that information also, we can complete the two-way MANOVA analysis also. So, let us go to two-way MANOVA model. Right here, so now you know that here we must have two factors. right. So, a factor A or factor 1, say factor A with has A levels, factor B has B levels, say. So, if we try to draw parallel with our real life data example, what you can say is, say factor A is the ownership factor, then it has how many levels? Well, A is equal to 3 here, because we talked of 3 types of ownerships. Factor B, say, is the certification factor. This also has 3 levels. This is not necessary that A and B can take different values, but this is coincidentally, this is all, B is also equal to 3 here, because we have talked about 3 types of certifications. But one thing here we consider is that we have n independent, at least initially we have n independent observations can be observed or can be collected or can be monitored at each of the, so it is a two-way classification, and there is AB such types of classes. So, I have at each of the AB combinations. Okay, of the 2 levels, AB combinations of the 2 levels, right. So, my data vector x, I, j and k, I need a third subscript, and this is nothing but the kth random vector or random observation corresponding to the ith level of factor A, ith level of, now I will simply write ith level of A and jth level of B. So, that is the situation I have, and that is why there are 3 subscripts I, j and k, the kth random observation corresponding to the ith level of A, jth level of B. So, I know that I goes from 1 to A, because I have said that there are A levels of factor A. Then j goes from 1 to B, because there are B levels of the second factor B, and k goes from 1 to n, because for each of the AB combinations I have n independent observations. Okay. Again, I assume a very simple model for the MANOVA, this analysis, and I have x, I, j, k. This is mu I, j plus this is the mean effect part and the error part, right. So, with expectation of x, I, j, k is mu I, j, and hence implying I have this error having mean vector is the null vector. Moreover, for the inference part, I have some distributional assumption. I use the assumption that this is following a p-variate normal distribution with mean as the null vector and the variance covariance matrix as sigma. So, mu I, j is, let us concentrate on this part and try to split it up into the different factors. So, this mu I, j is the mean effect due to the ith level of A and jth level of B, and let us see how we handle this. So, as before, I bring in an overall effect or the grand mean part, that is mu, and denote it by mu null null, okay. And then we have, this is how the adjustment goes. I have mu I naught minus this grand mean effect, then I again put a mu naught j again with the minus of overall effect. Now, since I have already brought these factors, what is the adjustment that I have to do finally? I have to consider a mu I j here, then I have to take out a mu I naught, I have to take out mu naught j, and since the overall effect has come twice with a negative sign, so I must put a plus mu naught naught here. I use some special notations for this. Mu naught naught is replaced by the usual mu as in the one-way MANOVA case, the overall or the grand mean effect. Now, there we had only mu I minus mu, which was the tau I. Here it is mu I naught minus mu naught naught, and this is, say now, alpha I, and for this I have beta j, and this is giving me the, let us use some another notation, gamma, and depending on both I j, and this basically this gamma I j part has the interpretation of the interaction effect of A and B, factor A and factor B. So, let us just describe all these terms, that parameters that we have introduced. So, where mu as before is the overall or grand mean effect, then I have alpha I, which is effect due to the ith level of A, beta j is the effect due to the jth level of B, and gamma ij is nothing but, if you have a look at it, it is mu ij minus mu I naught. Let us go back to it and see what is this. This is gamma ij is mu ij minus mu I naught minus mu naught j plus this. So, this we have already introduced as the effect due to the jth level of B, and what is the rest of it? Well, this is nothing but, so I have this, let us also write it in the parameter form, it will be easier for us. This is mu I naught minus, this comes in the subscript, so mu I naught minus mu naught naught, and then it is mu naught j minus mu naught naught. Is this, sorry, this is going to be mu ij, the first part. This is not alpha I, what I have written here is alpha I, this is not the first part of gamma ij, it is mu ij minus mu I naught, and then it is mu naught j minus mu naught naught, that is okay. So, this is, here you see here I is fixed, and I am taking out this mean effect from the j, from this mu ij. So, basically it is, what remains is the effect of jth level of B, but not overall, at for a fixed I. So, this is at ith level of A, ith level of and then this is nothing but the effect due to the jth level of B, and this is essentially, we denote this as the interaction effect between ith level of A and jth level of B. So, now I can write so that the two-way MANOVA model is, you have xij k, again the kth observation due to ith level of A, jth level of B, this is equal to mu plus alpha I plus beta j plus gamma I j, and finally the error term E I j k, with the very important assumption that this is a multivariate normal, and you have I from 1 to A, j from 1 to B, k from 1 to n. And what's more, we have also those constraints, because we have defined this alpha I is nothing but, if you recall, it is mu I naught minus mu naught naught. So, similarly for beta j and gamma I j also, we had something in the background. So, all those factors are giving me some constraints, which are just like we had in the case of the one-way MANOVA. Here we will have more such constraints. So, these are sum of alpha I over I from 1 to A. This sum is equal to sum of the beta j, sum over j from 1 to B. This is also equal to sum of gamma I j. Keep I fixed, take sum over j from 1 to B, or consider the other type of sum gamma I j. By their definition, if you check, it is very easy to do so. You take the summation, keep j fixed, and consider the sum over I from 1 to A. All of these are equal to 0. So, this completely describes my two-way MANOVA model, and then what we do is we split the data to get the sum of squares and cross product matrices. So, this is split the data from the random vector, we come to the data. So, this is small x I j k. Equivalently, we write it as x naught naught bar, then x I naught bar minus the overall sample mean. We have 3 subscripts here. So, this is going to be x I naught naught, here also 3, and then we have x naught j naught bar minus this, and then we have to do some adjustments here. We have to write x I j naught, bringing in these terms, and then because we have already defined what our alpha I, beta j and gamma I j are, we also have a clue as to how to get these terms here, because these are essentially the estimates of those parameters. So, gamma I j naught and then gamma I naught naught bar minus then gamma naught j naught bar, and I also put the overall sample mean, so that what remains is x I j k minus x I j naught. So, we proceed with the calculation of the sum of squares cross product matrices, and so sum of squares cross product matrix decomposition. We start, as in the one-way case, we start with that within the total variability of the data, and that is, now we have sum over 3 such things, x I j k minus the total variability. So, I have the overall mean and x I j k minus x naught naught transpose. This is equal to the first, for the first one, let's say I am keeping sum over I. So, the other two factors are coming, n for k and b for j, and what I have is x I naught. So, I have taken already summations over j and k. So, these j and k have vanished now, and I have x I naught naught bar x overall, and then the transpose of this. Next, I am considering leaving sum over j, which means I have taken care of sum over I and k. So, I have n and a here, and then I have factors x naught, j naught, and the triple zeros are coming this one. At the next step, I consider sum over k, so that I and j are remaining here, and then I have for n, and then xi j naught minus xi naught. So, x naught j naught and the same terms, let us write it x I j naught minus x I naught naught minus x naught j naught plus the overall sample mean with this. And finally, I have to have a triple summation, because what I am trying to do is trying to write it in these 4 factors. So, these have been deliberately, it has been split up into this form, because I already have an idea about the sample estimates of the parameters, and after adding and subtracting all those extra factors, what remains in the end is xi j k minus xi j naught with xi j k minus xi j naught. So, this splitting is giving me, let us denote these matrices by letters. So, this is total, the sum of squares total sum of squares and cross product total matrix. So, this by T, then the first one in the right hand side by A for the factor A, the second one is B for factor B, and the third one, this is the interaction effect. So, let us write AB for this, and the last one is for the residual. So, let us write E for this, and then we can, from here we can form the two-way MANOVA table to complete our analysis. So, each of these matrices can be calculated without any problem, and hence we have the two-way MANOVA table. First is of course the source of variation, then the degrees of freedom, then the sum of squares, cross product matrices, and next we will talk about the hypothesis, test statistics and test procedures. So, first source is due to factor A, source of variation due to factor A, then factor B, then the interaction AB, then we have the residuals, and all these are adding up to the total variability present in the data, the corrected total. The degrees of freedom, because we have the first constraint that sum of alpha I that is equal to 0. So, I have a loss of 1 degrees of freedom here, giving me A minus 1. Similarly, for factor B, I have loss of 1 degrees of freedom. So, this interaction has degrees of freedom A minus 1, product of these 2 degrees of freedom. Total I know has to be A, B, N minus 1, and hence the residual degrees of freedom is A, B times N minus 1. The sum of squares cross product matrices are A by my notation, this is B, this is AB, the residuals is E, and then this is T. I am going to test the test procedures for testing various effects. Now, the first hypothesis here, the first null hypothesis here, quite obviously, quite logically, is that we have the equality of the interaction effects, and this is equal to 0. So, this, if that is equal to 0, this is accepted, then we will move on to the next group of hypothesis, where we can test for the equality of means of the two factors separately. So, at the first stage we test that gamma 1 1. In this way I go to the last one, that is gamma AB, that is the last of factor A and last of factor B. These are all 0. This is absence of interaction of the two factors, and for this the Euler test rejects H naught if this, well, I have the residual part, that is the within matrix for me. I am not using the bracket here, so let us just leave it at E. This is a test statistic. And the between matrix here, this role is getting played by because I am testing for the interaction effect. The within is always the residuals, so sum of squares and cross product matrix residuals, but the between role is being taken over by the AB matrix. So, this is getting divided by, so basically I have to put a determinant sign actually, and then we have E plus AB, determinant of this, and this is, let us denote this by lambda AB star, this is small. Okay. The asymptotic test can be, we have minus n of log lambda AB star, this converges to the chi-square with P, and corresponding degrees of freedom, that is A minus 1 and B minus 1, or the Bartlett's test, where I have a slight modification here. This is AB n minus 1, which is now the total number of observations, and then I have its AB n minus 1, the total n minus 1. So, that is the degrees of the degrees of freedom for the total sum of squares total, and then we have minus of P plus 1, A minus 1, B minus 1, this by 2. So, this is slightly different from what we have in the one-way analysis case. The correction factor here is in fact AB n minus 1, and this is with the log of lambda AB star. This also asymptotically follows the central chi-square with P A minus 1 B minus 1 under H naught. So, we are going to find the value of this. Since we know the matrices, there is no problem in calculating this Wilks lambda criterion, and then we go for the next level of test, that is, if H naught 1 is accepted. We all know the test procedures. Now, if this is accepted, that is, there is in fact no interaction, we test for H naught 2, that is the equality of the different levels of the factor A, and these are now tested separately, beta 1 to beta B. Now, in fact, I can say that this are equal and also equal to the null vector, because what we are essentially testing is mu I minus, if you recall that how are these alpha i's and beta j's are defined, right, and the constraints that we have, if these are all equal, they must be equal to 0. Similarly here also we can mention this in our one way ANOVA as well, if we have not mentioned it already there in the hypothesis part, wherever we are writing the hypothesis, because we have the constraint, it always enables me to write that this is equal to 0. So let us just go back a few pages, and this is for the MANOVA, this is for the ANOVA case. I have the constraint this. Right here we can mention these are for the equalities. We are obviously not going to write equal to the null vector, but since we have come to the constraint that some of these are equal to the null vector, we can always write this as 0, and at least one inequality. So this can be actually corrected by writing at least one is or no inequality. That's fine. At least one inequality, not a problem. Right, that's all. So let's go to our last part wherever we had stopped. Because of the constants we can write this, and then for testing this hypothesis, the second hypothesis after the acceptance, well, it needs to be mentioned here, if the third one, if the first one is rejected, that there is some interaction effect, then there is no point in testing that these effects are, that there is no effect and these are all equal to the null vector. Okay. So if that is accepted, if H01 is accepted, then when only we go for H02. Obviously this has no bearing with the other group, that is, even if this is H02 is accepted or rejected, we will go and check for H03. So this for the first part, that is for H02, we reject so we can write this as reject H02 if determinant of E, the within matrix, and now the between matrix is nothing but the A matrix. This we denote by lambda A star is small, and reject H03 if determinant of E by determinant of E plus B, that is lambda B star is small. For the second one, that is for H02, I can use that n lambda A star. This follows, asymptotically follows a central chi-square with P times A minus 1. We have P or sorry A levels of the factor A, or with Bartlett's correction we have AB n minus 1 plus P plus, sorry, this is a minus sign, common minus here, P plus 1 minus A minus 1, the correction factor by 2, this with log of, we missed a log here, minus n log lambda star A, log of lambda A star. This follows the same chi-square with A minus 1 under H02, and for H03, the third one, I have minus n log lambda B star following chi-square P B minus 1, or with the Bartlett's correction I can use AB n minus 1 minus P plus 1 with B minus 1 by 2, this with log lambda B star. This follows a chi-square P with B minus 1 under H03. So I can find the values and immediately get the test procedures, I get my decisions, and next what I do is I list down the exact test situations that are available. So let us say that the degrees of freedom, say let us define this as the degrees of freedom for the sum of squares cross product matrix due to the interaction effect. And let gamma 2 be the error effect or the residual effect, and under the respective hypothesis, if we have situations like the dimension or the number of variables, the degrees of freedom of respective sum of squares cross product, then the test statistic and their distribution will quickly write down this. This is p equals 1, p equals 2, greater than equal to 1 and greater than equal to 1 also. So, the situation here is gamma 1 is greater than or equal to 1, gamma 2 can be anything, gamma 1 is greater than equal to 2, gamma 1 is equal to 1 and gamma 2 is equal to 2. So, for any value of the other, this is also gamma 1. So, this is for any value of gamma 2 and the test statistics are gamma 2 by gamma 1, 1 minus lambda star by lambda star of f gamma 1 gamma 2 under the null hypothesis. So, we are considering respective hypothesis, null hypothesis, and accordingly we are forming the test statistics. And for the next one is what we have is again this, note that these lambdas are going to be respectively AB or A or B according to the null hypothesis. So, we are going to complete this exact test table, and if possible we will go to a data example or we will continue with a new topic hence.